Good afternoon, everyone, and welcome to the CANDU Monark webinar hosted by NAYUGN in collaboration with AtkinsRealis. Today we are joined by so far 263 lovely individuals joining us online, as well as Patrick Reid, currently Technical Director at CANDU Monark. Today we will be learning more about the advancements of the CANDU Monark reactor, a Generation 3+ design that represents the next evolution of CANDU technology. So if we can move on to the next slide. Thank you. Now, we'll be discussing today's agenda. So in the beginning, I'm just going to go through an introduction on NAYUGN Durham, and as well as introducing our speaker, Patrick Reid. Then we're going to go through a land acknowledgement as well as a safety brief. Third, we're going to go through, Patrick is going to talk more about the CANDU Monark, which will run for approximately 35 minutes. Then we're going to leave 15 minutes at the end for an audience Q&A. Before we move on, I do want to kind of give some housekeeping rules. Number one, this meeting is being recorded. So by joining this meeting, you are consenting to be recorded. Number two, all the questions will be done through the live Q&A function, which you can find in the top right ribbon of the Teams meeting. And third of all, if you see a question you really like within that Q&A, be sure to like that question so that we're more likely going to see it and we're more likely going to ask Patrick about it. So we'll move on to the next slide, please. So we're going to start off with a short introduction to the NAYUGN Durham chapter. Created in 2008, the NAYUGN Durham chapter provides the opportunities for a young generation of nuclear enthusiasts in the Durham region to develop strong leadership and professional skills, create lifelong connections, engage an informed public, and inspire today's nuclear technology professionals to meet the challenges of the 21st century. NAYUGN Durham has several teams hosting events for networking, professional development, community outreach, and public relations/education. Our next event is a Lunch and Learn on the Nuclear Waste Management Organization on Wednesday, April 23rd from 12 p.m. to 1 p.m. at the PNIC. We will then be having a tour of the NWMO Oakville facility on Thursday, April 24th. Now, after we've introduced NAYUGN, we're going to move on to introducing our speaker, who's going to be Patrick Reid. So if we can move on to the next slide. Going to be talking a bit more about Patrick's background, and then I'll be introducing him. So Patrick Reid began his nuclear career in 1987 with a co-op work term recommissioning safety systems at Pickering 1 and 2 after their retube outages. He joined Ontario Hydro on graduation and then moved to New Brunswick as a consultant and eventually became a partner in Candesco Research Corp, which provided consulting and engineering services for the Canadian nuclear industry. He later joined AECL, now AtkinsRealis Nuclear Canada, in 2006. Since then, he has held various management roles, starting on the ACR 1000 project, with notable subsequent roles being management of reactor physics, deterministic safety analysis, and reactor core design safety and licensing, as well as being the engineering director for the CANMOX EC6 and the secondment to Moltex Energy. As a technical director on the CANDU Monark project, Patrick now has the overall responsibility for fuel design, physics, safety analysis, and licensing work on the CANDU Monark standard plan design program. And if you don't mind, Patrick will also be giving you the responsibility of taking over the rest of this webinar. So I'll pass it on to Patrick Reid, who's going to start us off.
Okay, thanks a lot, AJ. So if we can get the next slide, I'll get into this. So what I'm going to go through here is the CANDU Monark design description. I think the deck was circulated in advance of this meeting. I'm not necessarily going to hit every slide. I'm going to try to focus on what I think are some key points. I want to make certain that we leave time at the end for the Q&A part. I do sometimes get a little bit overly excited anyway, so I'm going to restrain myself at least in that way. So can we go to the next slide? Okay, so first I want to do the land acknowledgement. I'm not going to read. This is our standard land acknowledgement that we give here at Sheridan Park. That's in respect to the location where we do our work. I'm not going to read it. Everyone can do that. I'm just going to comment that, the facts that we acknowledge in our land acknowledgement are some of the facts that underpin the reasoning as to why Canada has affirmed the UN Declaration on the Rights of Indigenous People in Canadian law. So among other things, this means that if and when there's a a new nuclear project using this design that we're talking about today, the CANDU MONARK, and that project affects the lands, territories, or other resources of some Indigenous peoples in this country, that project will have to obtain the free, prior, and informed consent of those communities. It's, that's really a reflection of, these facts, among many others, are part of the why of that. Anyway, with that being said, let's move on to the next slide if we can. So this is a safety moment. For safety moments, I really like to do historical events, accidents that have occurred in the past, or near misses that illustrate important things about nuclear safety. So this is one that I find is sometimes little known, which is the accident that happened at SL1 in 1961. The anniversary was January the 3rd. So this was a natural circulation BWR, quite small, 3 megawatts thermal. It was intended to be, it was a prototype for a military SMR for remote military installations. The reactor was shut down. They were doing maintenance on it. And for some reason, the control rod was manually lifted. Manual lifting of the rod wasn't that unusual, but the amount that it was lifted was quite unusual. It was lifted 3 or 4 inches higher than its normal critical, the position that would bring the reactor critical. As a result, the reactor went significantly supercritical, 2% supercritical. That's about $3, well, massively in excess of the prompt critical threshold. And in LWRs in particular, that's a very bad thing to do. When you go super prompt critical, the reactor period drops to an extremely short period amount of time, 4 milliseconds. So what that meant is that the power increases were like this. So the reactor power reached 20,000 megawatts. This melted and vaporized even some of the fuel before eventually the thermal expansion from the heat up and the void formation terminated the transient. But this was a massive amount of power. It shot control rods out of the reactor, impaling that operator to the ceiling of the building, killing him. It also caused 2 other fatalities of the only other 2 people who were in the room. There was the energetic reaction lifted the pressure vessel 9 feet into the air before it dropped back into its original position. So it's amazing. So there's a link there for a briefing film that was put together by the Atomic Energy Commission in the States in the 1960s. I highly recommend watching it. It looks like something that whatever Tony Stark's father in the Marvel universe would have put together to explain some science thing. And there's a couple of particular spots that shows a real-time animation of the events and then a slow motion version of the events, and it explains not only what happened, but then also the cleanup. It's really, really cool. So highly recommended. What this illustrates, though, is the importance of this particular fundamental safety function of controlling the reactivity and the reactor power. We often talk about 3 C's, although there's more than 3 safety functions in the Canadian context, but it still boils down to control, cool, and contain. And it just really emphasizes the fact that control, if you don't have control, you don't have anything. Next slide, please. Okay, so, but we're here to talk about CANDU MONARK specifically. I won't say much on this slide other than what it shows. I will mention that the 3 different stations that are pictured here are very important because they form the real, in metal, you might say, antecedents of CANDU MONARK. You've got Bruce and Darlington at the left and center, which are the 480 channel, they're multi-unit CANDU stations here in Ontario. And there's also the Qinshan CANDU 6, the most recent start of construction CANDU units. There was a CANDU that came into service after the Qinshan units came into service, but that was a delayed construction project. But these are really the design antecedents of the CANDU MONARK. It can be seen as emerging and then an extension of the designs you see before you. Let's move to the next slide. So this is a very, very generic slide. Anyone who's done anything with CANDU has probably seen a slide very much like this. Just lays out what the different parts of a CANDU are. CANDU MONARK is nowhere different at this level. You've got a reactor inside the reactor building. It's a pressurized water reactor, only better because it's a PHWR. With the steam feeding a turbine generator and making electricity. Let's move to the next slide. So one of the things that people sometimes, this is a description of some of the key design features of CANDU Monark, but I will say that many of these apply equally well to any CANDU. It's just that CANDU is more so. So what I'll emphasize, I'll go over it, but I'll emphasize the things where we're more so. So when it comes to inherent safety characteristics, most of these are things that all CANDUs have. Having the low pressure moderator, having small reactivity coefficients overall, and a long reactor period. I mentioned that thing about SL1. In a CANDU reactor, if you exceed prompt critical, you don't have this order of magnitude, multiple order of magnitude change in reactor period. Increasing supercriticality always reduces reactor period, but it happens much more gradually in a CANDU. And that's something that's true. Having a 2-loop figure of 8, that's most CANDUs, not absolutely all of them, but that minimizes the amount of voiding that can happen in any loss of coolant event. Large containment, that's a typical CANDU thing. CANDU Monark is, I would say, one of those things that's more so. The relative size of the containment to the reactor power is more so than for existing CANDU designs, which brings a measure of inherent safety. Passive safety features are dual shutdown systems, are passive safety features that we have. The fact that a design basis accident does not result in a loss of coolant accident is unique to CANDUs, is another passive safety features. There are many passive means of cooling provided in CANDU Monark, like in many CANDU reactors. Most of them have at least some of these kinds of features. The one that is most, that is novel to CANDU Monark would be the reserve water tank and the way it's used in our design. The robust containment, this is another point that's a lot, significantly more so for CANDU Monark. We have more events included in our design basis in terms of pressure. And also the CANDU Monark containment design is designed for aircraft impact, including malevolent aircraft impact. Accessible, CANDUs have, depending on what design you're comparing to, a very high degree of accessibility, including on power accessibility, but this has also been enhanced, and the ability to move around and to do on power maintenance, we've further optimized in the way we've laid the facility out. The flexibility thing that we talk about here in terms of the online fueling and this is one that is the same for CANDU Monark as it is for any design. Operator friendly, that's another area where we're trying to improve, but CANDUs are operator friendly, pioneered digital control systems, for example. Our lifespan is lengthened relative to existing CANDU Monarks. And optimized construction and delivery, we're really leveraging experiences that we've had in the past, most particularly with Qinshan, which I'll talk about in a bit. Let's move to the next slide, please. And the next, again, I'm not going to talk about this. It's licensable. This is a Canadian reactor developed in Canada to be licensed in Canada. And so that is the basis for our very high confidence in the fact that a CANDU is going to be able to get a license. Can we go on? There's a pretty picture of a kind of an artist's rendition of what a 4-unit CANDU Monark station could look like. Let's move on again. So let me talk about the high-level picture of what this machine is. So people who know the Bruce and Darlington reactors will recognize that gross output of 1,075 megawatts is higher than the 935 that Darlington gets, for example. I'll talk about how in a bit. This is a Generation 3+ reactor. We are designing it for a 3-year outage cycle. So, you know, we are all, and quite rightly, proud of the Darlington unit that holds the world record for continuous operation. That's going to be the design basis for CANDU Monark. We'll have a 25-day outage duration, the 70-year plant life with a 95% annual capacity factor and 93% lifetime. The 93% really accounts for the midlife refurbishment. The 70 years is not, by the way. I saw a thing in the Q&A in advance, so people know. It's 35 years of operation, then a year and a half for the retube outage, and then another 35 years of operation. By the way, this leads to one of the things I like to do to get myself really super excited about CANDU Monark. So if you consider that we're developing CANDU Monark in the hopes that it'll be used in support of our net zero build out, and let's just assume that we're super successful and super fast and we get the last CANDU Monark that we need to get built in service by 2050. If that happens, and if that CANDU Monark gets a second retube, which I don't think is an unreasonable expectation, it will operate for 108 years. That means it would operate to 2158, which is past the bicentennial of the invention of the CANDU reactor in 1957. That's when they made the decisions to go to a horizontal pressure tube reactor. Before that, they were thinking of a pressure vessel. So when I think about that, I get all excited and I jump up and down. Okay, going on. It's designed to a high seismicity, much higher than has been applied in previous CANDU designs. This makes it, for the standard plant, this makes it more broadly deployable across a multitude of sites, although there are limitations. There always are in any standard plant design. Modular, the co-production of medical isotopes, we've tried to enhance the way the facility is laid out to make that easier and more possible in a CANDU without losing any of the things that already make CANDU awesome from this perspective. I won't read the other slides because I want to keep moving, so let's go on to the next, please. This is a very high level overall description. So as I mentioned, it's a 480 channel core, very similar to Darlington. It has a 2-loop heat transport system similar to a lot of designs. The CANDU 6 has a 2-loop figure of 8, so does Darlington. The ACR 1000, when it was developed, had a 2-loop figure of 8. It has a bunch of improvements to meet various drivers. The modularized construction I've mentioned. It uses all of the 480 channel reactors in Ontario were originally designed to be fueled with 13 bundles and fueled against the flow, although the Bruce units have been changed over to fueling with the flow with 12 bundles. CANDU Monark is 12 bundle fueling with the flow, slightly different than Bruce because we're going to position the fuel string so that it's properly centered in the flux. At Bruce, they have what they call the water bundle because at the outlet end, the bundle string still starts where it was going to start when they designed for 13. We will be using 37M fuel, the same fuel type that's used currently at Bruce and Darlington. Although all of the fuel cycle flexibility things about a CANDU is just as possible for CANDU Monark as it is for anything else. Our fuel handling approach is similar to any CANDU. The specific fueling machines that we use are based on the Bruce and the Darlington fueling machines. We have the same basic set of safety systems with some additions. We have second crash cool down, which I don't think is common in the Ontario reactors. We have the severe accident and heat removal and heat recovery system, whose acronym is terrible because it sounds like a deadly disease, but it's SARS. We have our containment system. We have a separate backup to containment isolation and the ventilation isolation system. We have this reserve water tank that I've alluded to once before, and emergency filter containment venting, which has been added on to most CANDU reactors, but wasn't an original part of CANDU design. And I mentioned that reserve water system is very important in terms of us having passive cooling for beyond design basis accidents. So it really improves our design extension conditions story. Can we move to the next slide? I'm not going to say anything on this slide, so let's move on to the next one while I unlock my screen that just locked on me. So one moment, please. I can't read the slide until I unlock. Long password. Okay, I mentioned the power. No CANDU has operated at this power before. And how do we get there? So there's 15% higher gross electrical power than Darlington. 1/3 of that is due to the improvements on the secondary side. So I won't say any more about it than that. The other 10% of power increase is divided broadly between two major contributors. One of the major contributors, the largest of them, is that we have flattened the core power distribution so that the peripheral the average channel power is closer to the maximum. The other 1/3 of the difference is adding about 3% to the total reactor power. So this is after, you can think of it in two stages. First you flatten and then you bump it up just a little bit, 3%. So that means that the highest channel power also goes up a little bit. So we compensate, in order to compensate for both of these things, the CANDU Monark has a much different, not much different, but significantly better heat transport system than, say, Darlington. The pump motors are somewhat bigger, although it's the same basic pump. The steam generators are very much bigger than in Darlington. So you have a much better heat removal machine attached to the core. So those improvements in the heat transport system help to mitigate the effects of pressure tube creep. And it really enables the slightly higher power limits by maintaining a very an excellent margin to dry out, even at end of life. And when it comes to bundle powers, we're still within the sort of historical experience of CANDU reactors in terms of bundle power limits. So that's how we get there. The whole point here is to stay within our experience base, but to make the design work better, in a nutshell. Let's go to the next slide. So we have the longer life that I mentioned. I said most of the things about this, but of course, this means that many components have to be designed in support of that duration. Things like fuel channel elongation, you need to have the right to bearing lengths. You need to consider the impacts of pressure tube creep appropriately. We'll say the heat transfer system is laid out and very similar to, say, Darlington. And really, we've optimized the fuel channel design. It's extremely similar to the fuel channel design at Darlington and CANDUs in general. But we have considered all of the limiting degradation mechanisms and made sure we've given ourselves the maximum ability to have fuel channel life management in support of this longer life and higher capacity factor together. You're almost at 300,000 effective full power hours, which is quite a while. Next slide, please. I mentioned the high seismic capacity. The thing that I'll mention, I said that there's limitations. We're using the design requirement in CANDU Monark is 0.33 Gs minimum, but the spectrum, the distribution of the accelerations as a function of frequency is one that's suitable to Central and Eastern North America. That means it's not representative of what you would see at a site that's very close to a fault, where they have a higher concentration of accelerations at lower ground frequency motions. So if one wanted to locate a CANDU Monark at a location like that, one would have to do some additional design work and maybe implement some design changes from the standard plant that we're developing. Next slide. But I will say that the seismic design basis for CANDU Monark is fine for any location that is being considered, for example, in Ontario. The fuel channel design, as I said, is very similar to CANDUs in general. Improvements that are predominantly in the way it's analyzed, but there are some details in the fuel channel design as a whole, and things like the spacer, the Clander tube, that are slightly tweaked to help us support avoiding the key degradation mechanisms within the expected plant life, and also changes to control things like deuterium uptake, because deuterium and hydrogen embrittlement is a very important consideration, and that can be limiting to fuel channel life because it's a zirconium alloy component. Next slide. The reactor assembly, I'm not going to say too much here because this is very CANDU standard, except to emphasize that the Bruce and Darlington reactors use what's called a shield tank, which is a metal tank around the calandria full of light water. CANDU Monark is more like the Pickering B units or the CANDU 6 unit, where the calandria is inside a concrete vault full of water. The concrete vault makes it easier to design for high seismicity because it's more structurally robust. And both of those things, the vault or the shield tank, provide another body of water for which in severe accidents is an important passive source of cooling. Aside from the fact that both of those things, as the names imply, provide shielding. Next slide, please. Reactor control is done in a CANDU Monark the way it's done in any CANDU reactor, so I won't say anything more. Let's move on. The fuel design, as I mentioned, is we're using an existing fuel type, which isn't a limitation. Every single CANDU can use all different kinds of different fuel and different carriers, and it's important for people to understand that we even have experience right here in Ontario. In the very first commercial CANDU, NPD, they used MOX fuels, which were a combination of low-enriched uranium and plutonium on a demonstration basis. We've done demonstrations of CanFlex fuel at Bruce with low-enriched uranium and neutron-absorbing central element, and there's all kinds of things you can do with a CANDU reactor. As people like to say, if you can run on dirt, you can run on anything, and that's true for CANDU Monark. Next slide, please. On power fueling, not a lot to say here. Two fueling machines, as I said, they're based on the Bruce and Darlington ones. One difference from Bruce and Darlington is those reactors, you'll have 4 units altogether that share 6 fueling machines. So it's 1 1/3 fueling machines per reactor, if you want to put it that way, although of course they're always used pairwise. In CANDU Monark, there are 8 fueling machines in service when the reactor is operating, a pair dedicated to each reactor. This is something that we leverage to the maximum extent possible to ease the burden. You know, on-power fueling is the great strength, but also the great challenge in a CANDU reactor because, yeah, it's awesome. You don't have to shut down for a refueling outage every however often. But on the other hand, it sucks because you've got to fuel every flipping day. So one of our goals in CANDU Monark, which will never be fully achieved, is to make the job of being on the fueling team, like being the Maytag repairman, you know, the guy who never gets to go to work. And that's never going to happen. I know every fuel handling guy I've ever known in my life has a boat and a car and a cottage because they're always maxed out on overtime every year, right? But we're going to try to reduce that a little bit. Next slide. Here's something that is more different, the way it's laid out. Because the fuel handling is fully unitized in CANDU Monark. So relative to what you would see at Pickering or Bruce or Darlington, this is a lot more similar at a high level to what you'd see in a CANDU 6. There is the fueling machines do not go outside the reactor building. New fuel is transferred into the fueling machine. It goes straight to the reactor face, does the refueling, and then discharges directly into there's a reception bay on either side, so you can discharge fuel from either side of the reactor, but it's all linked into one overall very seismically robust structure that's all connected together, but with one big storage bay. The auxiliary bay that's noted there is for storing things like control rods or other things that you might pull out of the core separate from the fuel. One of the things to emphasize is that the way the facility is laid out is designed to make it straightforward to pull out a fueling machine head and replace it with another one if there are problems with fueling. And then, so if you're having a problem with the fueling machine head, you swap in the spare and then you fix it offline, away from the issue of having to fuel every day. Next slide, please. The moderator system is very similar to any CANDUs with a couple of differences. The heat exchangers are not vertical, they're laid out horizontally. And there's 4, inconsistent with our 4-quadrant approach, which I'll talk about later. The only other thing that I will say is that the moderator system as a whole is seismically qualified to the full design basis earthquake. Existing CANDUs that exist around the world are qualified to a fraction of dBA. Sometimes it's a quarter, sometimes it's a third, because of the fact that of the perception that a seismic losing inventory from the moderator in a seismic event, because the heat transport system stays intact, is really only an economic issue. However, as time has gone on and we've looked more deeply and had more robust expectations in regards to severe accidents and beyond design basis events, seismically qualifying the moderator system brings benefits in that front. So that's what we're doing for CANDU Monark. Next, please. The heat transport system, not a lot to say because it's very similar to stuff that we said before, so let's move on. Control room is all modern and new, and that's going to be true for any new plant all the time, so I'm not going to say too much more than that. Let's move on. Secondary control room. There's always a secondary control room in CANDUs. This control area, this is more robust, in line with more up-to-date expectations. So let's go on again. The digital twin. A digital twin is something that an operator has. When we talk about digital twin, what we're saying is we're trying to do all of our work so that all of the material needed for a digital twin is there, right? We're trying to design this thing in the 21st century, to put it in a nutshell. Next slide, please. Enhanced health monitoring. This is very important to us achieving the very high capacity factor and to really leveraging the online maintainability and the flexibility of a CANDU and the fact that you don't need refueling outages. If you set your systems up so you can do enhanced health monitoring, you can also better manage the maintenance requirements, ensure that equipment is in service at all times, and reduce the chance of forced outages for sure. And also leverage your ability to maintain on power. Next slide. The streamlined construction. This picture shows it all, but I will say, you know, one of the things, Qinshan is one of the fastest new build constructions ever. Certainly, it's the fastest one the Chinese have ever done. And a big part of the reason for that is the fact that we tweaked the CANDU 6 design as much as we could to enable open top modular construction approach. And it was so successful what we did for CANDU Monark, first for ACR, but then, and we've inherited this for CANDU Monark, is we've really doubled down on that and designed the plan from the ground up to be able to be constructed in a modular manner, modular manner to really optimize the construction time. Next slide. Keep going. And again. Okay, so safety systems are very similar to CANDU in general, so I'm only going to talk about a couple things in here. I will talk about the long-term cooling system and the emergency feed water system, SARS, and the low flow containment phrase, and also the 4-quadrant philosophy. So that's maybe half of the thing. So let's go next, please. 4-quadrant philosophy. What this means is that outside of the reactor building, where a lot of systems related to cooling primarily exist, it's laid out in 4 quadrants, and you only need 2 of the quadrants to work to meet all of your safety criteria. That means you can take a quadrant out for maintenance on power, and you're left with 3. And then, even then, if an event were to occur, you could have one of the quadrants go down because of the single failure criterion, and you would still meet all of your safety requirements, right? And it means each one of those trains does not have to have a bunch of redundancies built into them, because the redundancy is provided in broad. That's the basic essence. In addition to that, we've got a 4-channel logic instead of a 3-channel logic. The purpose for that is to make it easier and less risky to take a trip channel out of service for maintenance, and you're then on 2 out of 3 logic, which is what we normally have in a CANDU anyway, but most of the time you're on 2 out of 4 logic. Next, please. Keep going. This is a little schematic of what that sort of looks like and how things are laid out outside of the reactor building. Of course, inside the reactor building, it's not 4 quadrants because you're inside the reactor building. Most of the systems inside the reactor building are singular systems, like the emergency core cooling system, ECI, I should say, or the shutdown systems. Next, please. Won't say anything about shutdown systems because CANDU Monark is a CANDU. Next, please. Emergency core cooling, ECI, is very much like any CANDU. Long-term cooling is the one that's more novel, so let's go to that slide if we can. So next, please. And the next. Most CANDUs have, oh, even one more. Here we go. Most CANDUs have an emergency core cooling system that has a long-term or recovery mode, and they also have a separate shutdown cooling system for when they're shut down and have to remove decay heat with the heat transport system out. That is fundamentally the same problem. So this idea first came out in ACR, but we've kept it for CANDU Monark. We have one system that can work in either one of those modes in response to an accident or in an outage. So that's what the long-term cooling system is. And as I mentioned before, it's provided in 4 divisions, any 2 of which can perform the long-term cooling function after an accident. If we go to the next slide, there's a high-level flow sheet that illustrates where it is and shows how what the division between light water and heavy water, because ECC uses light water, but of course in the long-term cooling mode, in a shutdown cooling scenario, you would only use heavy water. Next, please. The emergency feed water system is a little bit different than what we have in existing CANDU reactors. This is a safety system that provides water to the secondary side of the steam generators for heat removal. We can do it at full system temperature and pressure. That's it in a nutshell. Next, please. Once again, it's provided in 4 quadrants, but you only need 2. The last system, this is an important system. It's called SARS. This is our severe accident management system. And in a way, it's a little bit analogous to a long-term ECI system, except it can pump water back in almost anywhere. It can pump water, it can pull water from the basement or the sump, put it through a heat exchanger and put it back either in the calandria, in the vault, into the heat transport system, into the reactor inlet headers, into the steam generators for secondary side cooling if the heat transport system is intact, or into that reserve water tank at the very top where it can make up to all those places and run these low flow sprays that can maintain containment pressure low. It has provisions to hook up to an external water source or to the lake or to an external pump. If you have any version of SARS running, then you can cool containment indefinitely. Next, please. The containment system is very similar, as I said before, to any, not like the Bruce and Darlington units that have the multi-unit negative pressure containment, more like a CANDU 6 in general, or most water reactors around the world. It's stronger, more leak tight, higher pressure, more robust against impacts than previous CANDU. We also have hydrogen control as part of the containment system. And also, unlike most CANDUs, in addition to the normal containment isolation system, we have a backup for that for severe accidents in case the first one fails. This is really to make the possibility of containment bypass much, much lower. Next. The reserve water system I've already kind of alluded to, so I won't say more. I'm trying to be cognizant of the time. All of these safety systems need safety support systems that need to be sufficiently reliable to support the 10 to the minus 3 unreliability that any safety system needs to provide. These are they. The EDS, ECW, ESW, and the essential chilled water systems are all provided on a 4-quadrant basis, parallel to the systems that they support. Instrument air is not on a 4-quadrant basis because it's fundamentally local bottles of compressed air. Next, the essential instrument air is. Power is broken down in a way still very consistent with the standard CANDU approach with class 1, class 2, class 4, except that that SARS system that I mentioned has its own dedicated diesel generator independent of the others. That's the big point. Next, please. Okay, I made it to the end, and what do you know? I'm even ahead of time because I put on the afterburners. So what am I saying? CANDU Monark is very consistent with the CANDUs of history. You know, this is an extremely successful design. It's an extremely safe design. We've shown that it can be built cost effectively, it can be run cost effectively, and it can be run safely. Everything in CANDU Monark is intended to double down on that, to improve it without taking away those benefits and those observable truths. That's what a Generation 3, Generation 3 Plus, some people criticize, I have too, as being almost a sort of a marketing slogan. But what it means is when you've got something that's proven and working, you've made it better, more economical, and safer. That's what CANDU Monark is. So in order to do that, we've leveraged everything we know about CANDU. We've improved the output. We've improved the life. We've improved the capacity factor and made that achievable. This is reflected in the long outage cycle. You know, when CANDUs were first built, we used to spank LWRs all the time on capacity factor because they were shutting down every year for a refueling outage. It would take 2 or 3 months. Well, then they got good, right? Now they shut down every 18 months and it's like 18 days. So that doesn't mean that there's not an advantage in on-power fueling. It means you have to work it in the design. You need to make sure you can do the on-power maintenance on everything without shutting down. You need to make it so that you don't have to shut down as much as possible, right? If you don't have to shut down to fuel, get rid of everything else that makes you shut down as far as you can. And that's what we're doing in CANDU Monark. We've also enhanced the safety in many important ways. I would say that the most important things that we've done in CANDU Monark boil down to that high seismic capacity. And one of the things that you get with the 4-quadrant design is a much more robust story on fire protection, because if you look at the PSA for almost any nuclear power plant in the world, it's dominated by fire and seismic. Those are the hazards, the real hazards in nuclear. And that's the place where the most important improvements in safety can be made, in my view. We have a period of at least 72 hours after the start of an event that develops into a severe accident before you need to start evacuating people off site, right? Even if there's no operator action of any kind. We're also trying to develop it, like I said before, in the 21st century. We want to make it straightforward for a utility that picks CANDU Monark to have a digital twin and to get all of the operational benefits that brings and maintenance benefits that brings as well. So,
wanted to jump in. We have 2 minutes left before we move on to the Q&A.
Yeah,
but you seem to be on
this is
time,
my last
so,
slide.
Yeah,
this is it. So we're good.
Amazing.
So now, please, I'm open to questions.
All right. Oh, well, boy, do we have questions. With the 298 attendees in here, we've already had like almost 30 questions that we might ask. So the real question is, how much time do you have? That's
I don't have to go right at 1.
Yeah.
So let's just get into
Gotcha.
it. And when it gets painful, I'll say so.
For sure. Just blink twice. So First of all, I want to thank you for the very detailed and in-depth presentation. As a person who's starting out in the industry, I'm really excited, like for sure. As you can see behind me, I mean, I'm working currently on the SMR, and I joined because it's a brand new project and that sort of stuff. And before you know it, the Monark is being announced at the same time. And the second thing I want to mention is I really appreciate how you connected everything back to Bruce and Darlington, as well as Pickering, as I believe a majority of the attendees are working there currently. While we're on the topic of those three sites, we're all very familiar with what CANDU stands for, right? But Monark is a bit of an enigma. Is it an acronym? What does it stand for? What does it mean? If you could provide a bit more context behind that.
This is an example of non-engineers taking things over. There is no meaning other than it kind of sounds cool. The monarch is the guy who runs things, is the king or the queen, so that's cool. It makes you think of butterflies, so does the logo. Although I would say the thing I want to see someday is an animation of a butterfly landing, and then it morphs into that 4-quadrant layout, you know, with the circular of the reactor building, and because I think anyway. But Monarch, it's supposed to evoke feelings of things like that. Things like the butterfly implies environmentalism and blah, blah, blah. Monarch is like a leader or whatever. It's that sort of thing. Although someone, a friend of mine suggested that we should call it the modular nuclear AtkinsRealis kick-ass reactor. So I like that.
No, I agree 100%. I mean, for me, at least, it invokes power, right? And that's what we're generating in the end, right? So makes sense for sure. So the next question we're going to jump to is related to the first couple of slides that you mentioned. This person asks, how is a 25-day outage duration derived? And how would this present a significant improvement over current CANDU outages?
Well, the whole thing is in support of that 95% overall capacity factor. It's very hard to get to low numbers like this. That means only 5% of the time is it not operating at full power, right? So you have to make an allowance for force loss rate, which is the oh shit outage. So it depends upon an outage schedule. You know, we have design requirements for systems in general. It needs to be either maintainable on power, or have a maintenance frequency of 3 years or more. And then you have to schedule the outage so that you can achieve that duration. This is really tricky. And this is another place where the 4-quadrant design comes into play. A lot of the work sometimes in an outage is setting up your heat sinks. You go into the outage and then you set things up with your heat sinks, right? So then you can take stuff out to work on it. Well, if you've got a 4-quadrant design, you can do things like that in advance, because you can have worked on your cooling systems on power, right? Even your safety critical ones. Also, it means that you've got 4 buses for your essential supplies. So once again, you have a much higher degree of flexibility in terms of for essential loads than you do in an existing CANDU. So the ACR 1000, this is really leveraging things that were done in the ACR 1000. Now that had a shorter outage duration of only 20 days, but in CANDU Monark, we have some differences because of the need for heavy water management and things like that. So it's longer than we were claiming for ACR, but there's outage studies and outage experience that's behind that. This, of course, is the kind of thing that has to be fleshed out better and better and better as time progresses, but that's the high-level answer.
No, for sure. And I keep hearing again about the 4-quadrant design and how in of itself it's solving a lot of problems at the same time, right?
It has many advantages. I mean, it does mean that there's more equipment, but the systems involved can't, like the trains in the system can be simpler. You can maintain them on power, like, so it's not, you know, there's no put without some kind of get. You need to balance these things out. And it's important to remember that the 4-quadrant approach is really focused in only on the essential systems, the things used for safety, for accident response. Our plant cooling water and service water systems that are similar to what a CANDU 6 has are very much like RCW and RSW at Point Lepreau, only bigger. And the overall main power and control, it's still odd and even as in an existing CANDU, right? We haven't uber complicated everything here.
No, for sure. That moves us on to the next question, actually. What will be the core configuration of the CANDU Monark? And as an example, the number of adjuster rods, control absorbers, what is the fueling scheme, and what kind of isotopes are being considered within the design basis?
Ooh, big set of questions. Okay, so the core configuration, when you talk about devices, We have 16 adjusters, similar to Darlington, but not. Darlington started out with 24 adjusters, and then they went to 16. So their 16 adjusters are not quite symmetrically laid out. Ours are. Also, they started out with 24 and went down to 16. We're designed for 16 from the beginning, so our individual adjusters are a little bit heavier, which means that we still have the same. We have more negative reactivity available by withdrawing adjusters than Darlington has with their 16, but they're uniformly distributed. When it comes to shutoff rods and things like that, we're very aligned with Darlington. The liquid zone control, it's still 7x2. And I'm trying to think of the different things. When it comes to isotopes, the big thing we're doing in CANDU Monark, nobody has what we have, which is the low pressure access to a low pressure volume with a huge number of neutrons. That's the key thing for isotope production, and every CANDU has it. What we're trying to do in CANDU Monark is to lay the broader facility out. So getting in and out with flasks and with equipment is more straightforward. So really those are the improvements. So, and in fact, we're making CANDU Monark sort of isotope ready, flexible for a whole bunch of different systems and a whole bunch of different isotopes. So as it sits, you could do analogous systems to any of the systems that are used at Bruce and at Darlington or anywhere. Those are the main ones. Also, and cobalt adjusters, of course. But one of the things I said that thing about the 200th anniversary of the invention of the CANDU reactor. We need to think about this in the context of the isotope market too. I mean, if anybody has been to, I've been lucky to go to conferences where MDs are talking about medical isotopes, and I'm telling you, like, the future here is unbelievably limitless, I think. The important thing is to have a design that is flexible to be able to do whatever the heck, because believe me, these people are working on whatever the heck. And in 50 or 100 years, who knows what the heck we're going to be making. What we need is the ability to get targets in and out expeditiously, easily, without disrupting operation. And then the world is our oyster on that front.
Yeah, no, completely. Based on that piece of flexibility, I guess we could tie that in with modularity. Then, in that case, at the same time, as you
in a sense, so
mention,
they're serving two different kinds of flexibility. The modularity is really about ease of construction. The accessibility is about leveraging the fact that CANDUs have always had big portions inside the reactor building on power accessible, right? So we're also trying to lay things out so you can get in and out more easily, and when you get to equipment, you can get at it better. I'm not saying that there's not going to be cases where it's going to be a pain and there's not going to be some maintainer saying, who the hell designed this damn thing? But the expectation is that it'll be less for the CANDU Monark, because the reality is when you build any big complicated machine, there's some things that are hard to get at, but you need to optimize that. And we're trying to leverage experience. And we're really fortunate to have all of this operational experience of CANDUs to try and balance out the lessons and pick the best path.
Oh, absolutely. And yeah, I just want to peg on that modular construction piece that you mentioned. So I've got this question, it's a bit of a long one, so I'll just get started. So the design for modular construction will be great for speeding up installation, as you mentioned. But as the plant ages, it's expected that more large-scale maintenance will be required. Performing large-scale maintenance on existing CANDU plants has encountered issues where direct replacements are not possible due to size limitations in the access routes, resulting in the need for custom-designed modular components to maintain systems. What kind of consideration has there been in regards to large-scale maintenance of the CANDU Monark systems later in the life cycle? So perhaps after the retube that you mentioned, that's after 35 years. And for example, has verification been performed to ensure direct replacements of components can all be transited through the standard access routes?
So overall, yes, there are some components that can't just come out through the airlock. I would say the poster child for this is the steam generators. So make no mistake, CANDU Monark steam generators are being designed for a full 70-year life and to not be replaced. However, we're designing provisions in the design if you have to replace the steam generators to be able to do so. But this involves, when it comes to the steam generators, this involves having provisions to be able to open up containment, right, and raise them back out, for example. But other things like heat transport system pump motors, the moderator heat exchangers, things like this are designed to be able to get in and out. So those are some pretty big components, for example. They are designed to be able to get in and out of the reactor if they need to be replaced.
Gotcha. But looking outside the reactor, a person did notice that within the artist visualization that you showed previously, there wasn't a vacuum building. Is there a vacuum
This is
building
correct.
built into
CANDU
the design
Monark
basis?
is a unitized containment, like what you have for, say, a CANDU 6, not like any of the multi-unit CANDUs in Ontario. So and associated with that, the reactor building is designed. I alluded to high pressure, and CANDU 6s they design for large LOCA, but not main steam line break, because main steam line break doesn't lead to a risk of fission product releases from the core. However, in CANDU Monark, we include that in the design basis as well. So the design pressure will be, hundreds of kPa, at least something like 250 kPa gauge.
Mm-hmm.
And
Gotcha.
that's part of the design approach. We also have things like the low flow sprays. You don't need it in design basis accidents, but in severe accidents, you'll be able to use those sprays similar to the sprays in the vacuum building. And there are sprays also in designs like CANDU 6 to control containment pressure, to stimulate condensation.
100%. Yeah, no, then I want to move on a bit more from the technical questions, a bit more speculation on your end. We've got a question here. How likely is it that the CANDU Monark is the design of choice for Bruce C? So there's a lot of talk about what's going to happen over there. So we hope you could shed some light on that, and maybe your opinions as well, if possible.
I don't know, right? I mean, I suppose no surprise for a guy who's done his whole life in CANDU and who came to AECL in 2006 because he wanted to be in on the first new CANDU reactor design in a generation. I think it should be CANDU Monark, right? But it's not my call. I think there's a lot of considerations that go into selecting a reactor design, and I certainly believe in the case for CANDU. Right, all the things that we can talk about many times, like the original reason the CANDU was developed in the beginning, to have a design that to the maximum extent possible could be built, operated, supplied indigenously, is I think a huge advantage, and one that we should leverage whenever we can. And CANDU, I said it before, we've proven it can be built cost effectively, it can be run cost effectively. In my personal opinion, when you look at cases where there's been boondoggles, and every design has had its boondoggles, both in construction, like we've also shown that every design in the world can be constructed at a ruinous overspend and in a ridiculously long amount of time, and can be operated at, totally uneconomically. What's the difference? It's not about the technology, right? It's about the organization, the projects that do the construction, or the organization, and you could call it a project that runs the reactor, and doing that with excellence. Now, in Canada, we've got all the tools. What we need to do is we need to muster them and apply them. That's my own opinion in that matter, right? So, Bruce C hasn't made a decision. They're investigating multiple technologies, including CANDU Monark. OPG has talked about Wesleyville, and they said they want to do large-scale nuclear, but they also haven't selected a technology. There's the Energy Alberta prospect, where they have said that they want to do CANDU, but they haven't gotten to the point. Only one of these things has gotten to the point of doing an initial project description, which is the very first step of impact assessment before site license or anything, and that's Bruce C. That's currently, last time I checked, that was suspended at their request while they're doing some more activities before they resume. So, that selection, it's still early days in respect to these things. So, I think it's a slam dunk decision, but it's not my decision to make, right? Mm-hmm. So but what we're doing here is trying to make, every day we work to make that case we think a little bit more obvious, right? And then we can only hope that then that when the call gets made, we're the ones called.
Absolutely, yeah. And I just want to echo the piece that you mentioned about it being Canadian A to Z, right? And everything being able to be found within Canada of itself, whether it be the fuel, building the reactor itself, all the materials as well. But there's just one thing that was mentioned by the questions that would like some additional context on, which is the D2O inventory. As you know, we currently do not have any operational heavy water plants, at least the one that was in Bruce got shut down. So where will that inventory be coming from?
Well, we'll need to be building more. There are some supplies available, and there are suppliers. They're international. right? But I can't remember if it was earlier this year or last year. I mean, there's a whole nother thread of activity going on. AtkinsRealis is involved, CNL is involved about standing up domestic heavy water production again. And to me, particularly the picture I painted where CANDU Monark is the center of our net zero build out with, you know, multiple reactors being built over the next decades, kind of like what we did in the 70s and the 80s, then we're going to need a lot of heavy water and we will need to have that production. So that is another thread. It's another thing. I mean, I don't think there's any issue of doability in that. It's about doing the doable thing, right? But there are pathways to, as I understand it, to procuring the necessary heavy water for the first units if it takes us a while to stand up the indigenous production. And I should say, you know, CANDU is designed to be indigenizable to the maximum extent. Even I don't expect a CANDU Monark project to be 100.00% indigenous. I'm sure we will leverage international supply chains for things, right? But it's way easier to be way higher, right, than any other design.
No, for sure. And I mean, we're looking forward to potentially seeing if something gets built here locally. In that case, then we don't have to rely on those international supply chains, especially given the political climate as of
everything that's going on now.
Exactly.
It becomes a valid question. Yeah. Especially 100%. Since you know, when it comes to nuclear, one of the things that it's important, I think it's important to remember, is that the international trade in nuclear technology, including nuclear information, is not a free market. It is controlled by national governments, not by companies, right? If you want to export not just parts, but also designs about parts, things that fall under the umbrella of what we call controlled nuclear information, you need a license or a permit from the government that controls that technology, right? So when it talks about CANDU, that's Canada. Like when we do work for the Koreans at Wolsong, we need an import and export license in support of the information transfer, not just components, right? It's true for any nuclear technology.
No, absolutely. And you're mentioning all these benefits that we're hearing with the Monark, right? But we have a question here. It says, what are the downsides in comparison to Bruce Power and Darlington? But I believe a better way to rephrase it would be like, what systems currently exist that would be better than what is being introduced in the CANDU Monark? Or in your opinion, or otherwise?
Well, that's a toughie. In general, you know, across many CANDU, systems are very similar anyway, even if you look at designs as different as, say, the Bruce Darlington configuration in a CANDU 6, right? There's a lot of commonality. However, there are differences too. So I would say there are and some of these things I think I mentioned before that, you know, I was talking about 4-quadrant, and, you know, nothing is almost nothing is an unalloyed good. So let's talk about containment. One of the things that's come up, you know, we have unitized single unit containment, whereas all of the Ontario reactors have a multi-unit containment concept with a vacuum building, right? Now, a lot of people dunk on that concept in general. It's certainly true that it's unique to Canada, but in my opinion, I don't think there's anything wrong with it. It has weaknesses because you've got safety systems that are interlinked across multiple units. Outages and maintenance and things like that can be very problematic and hard to manage. But we've worked out ways to do it over the decades, right? But that whole negative pressure containment approach, right, is really very interesting and novel, and it brings benefits as well. So, you know, this kind of boils down to the fact that, you know, no one can ever claim, I don't think, they have the perfect design except maybe the wheel, right? Because it's simple enough, perhaps.
It's a pretty good one. I'm not going to lie, it's a pretty good one.
You know, a hugely complex piece of machinery like a nuclear power plant, right? You go one way, it will have benefits and it will have costs. And sometimes it becomes a bit of a less filling, tastes great kind of argument, right, as to what's better, in my opinion. I do think there was a very, very earnest attempt that's culminated in CANDU Monark for us to make those less filling taste great in the best ways we could, right? Like, let's not forget, the CANDU Monark is, you know, wasn't a design that started just a couple of years ago, right? If you look at its roots, you know, what I would now call the Generation 3 CANDU design programs started in the early 1990s at AACL. We had CANDU 3, and there are still features where in CANDU Monark where the conceptual design ideas are rooted way back there in the early 90s. CANDU 3, CANDU 9, the ACR, and the EC6, right? As well as the changes and improvements that happened in the parallel at that time, programs to improve the CANDU 6, right? Which was delivered after all of that program began. All of that comes into CANDU Monark. And over that whole arc of time, you know, there's been a continuous and diligent effort to try to make the best we could of those decisions. And we're still getting feedback to this day. We're engaging with Bruce Power and OPG to get feedback on design and to look for places where we could do it better.
Mm-hmm.
Right?
No, 100%. I appreciate the fact that you admit, even though it's a new project, there's still lessons to be learned, right? Even though the countless of hours being poured into it. Now, I want to kind of shift that aspect to based on projects that, you know, are already being built. And this is a very popular question. There is currently demand for SMR reactors. Is there a CANDU designed or CANDU-esque SMR getting developed?
You can't use that participle, getting, but there we have done work in AtkinsRealis to go back to, I mentioned to that CANDU 3 design, which was the CANDU SMR design that was being developed in the 1990s for jurisdictions like Saskatchewan, which is now interested in BWR X300. And that was set aside back in the 90s when we shifted to CANDU 9 and then into ACR. But a few years ago, AtkinsRealis did spend some time and money to sort of, I don't know how you would call it, to establish something that we call CANDU SMR, which is we laid the initial conceptual groundwork for a small, you know, a 300 megawatt version of a CANDU, right? And anybody I've heard a lot of people say, well, you can't make a CANDU that small. You have on power fueling, it requires staff. Yes, these are barriers for a very small output CANDU. However, I think we don't need to look anywhere further than India, where they started with 200. They are still. The last one came into service maybe 10 years ago. They're 220 megawatt IPHWR, which is a development of the original Douglas Point, but it is also a modernized design, generation 3 anyway. 220 megawatts that they have delivered very cost effectively. They build them in packs of 4 at least, and operating very successfully, right? It can be done. A CANDU at that scale. CANDU SMR is not that much like IPHWR 220. But I'm just trying to address that. It's the obvious objection, I think, to a small CANDU, but it can be done, and it can be done cost effectively. And so there has been work to establish that concept, but you know, AtkinsRealis sort of took a step back a few years ago and recognized that they made the call that they believe that the real long immediate opportunity was more focused in the large-scale nuclear space, and so then we were doing work that was focused on around the gigawatt size, as opposed to. And I think, you know, it's a lot to do. We have a lot on our plates, even in just the new build space between CANDU Monark, and we also have C34, which is not CANDU Monark. It's an evolution of CANDU 6. It's got a lot of EC6 features, and to also trying to be carrying forward a smaller CANDU design at the same time, I think it would dilute our chances of success too much. So, but the concept is there. That fundamental work has been done. So it could be done, could be picked up.
That's good to hear. Yeah, no, for sure. The more improvement, the better, right? Towards achieving net zero, at least by 2050. Now, you did mention packs of 4, right? Just like the SMRs being built in India, right? And currently, we do see CANDUs in groups of 4. Is there any efficiency gained for the Monark with this grouping, or could we, you know, see some other combination? So, like in the visualization that you had, we had 4, right? But is it possible to have 6 together, or 2 potentially?
Yes. The CANDU Monark, we're doing a standard plant design, right? So our basic approach, and this has been, you know, we inherited this from the AECL days. The basic approach that we've been doing for CANDU design is to conceptualize it in a 2-pack, which makes it very straightforward to go down to 1, deliver it at 2, or any other combination, right? CANDU Monark could be delivered in 1, 2, 3, 4, 5, 6, 7, 8. Who do you appreciate? I mean, it doesn't matter. So there is a lot of flexibility. CANDU Monark, when it comes to safety systems, is very focused on unitization to a very large degree, although there's still potential to tweak that a bit. But on process systems and production-related systems, we have done work to study where you can do the sharing, where you could gain some further efficiencies and maybe easings in operational and other burdens by in a multi-unit configuration, by sharing things across the whole station.
Absolutely. What a perfect way to round it up. Well, that kind of puts us at 10 minutes over. So we apologize for taking an extra 10 minutes of your time, but we did. Amazing. We hit a record 300 attendees with, I believe, over 70 questions being posed. Fortunately, we only got through like 20 or so, but I mean, as time progresses, I believe that most of their questions would be answered, given more and more technical information would start to be released later. But that pretty much wraps us up for this webinar. So I want to thank all the attendees for taking time out of your busy day to also attend, learn about the CANDU Monark. And I wanted to give special props as well to Patrick, not just thanks for being in the hot seat and answering these questions rapid fire as I was throwing them. I thought that was amazing and really shows how much confidence and how much enthusiasm, right, that you have for the CANDU Monark. And I want to say that I have the same thing, and I'd love to see more nuclear plants being implemented and more indigenous-based ones also being implemented here in Canada. That's about it. I believe all the presentations, in case anyone wants to follow up on, were included in the original meeting, as well as just reminding you that this session was recorded. So in case you want to follow up on anything, you want to hear anything again that Patrick mentioned, you can always access that recording. Other than that, I want to thank you guys for attending. Thank you, Patrick, for joining us and answering all the questions and going through the presentation. We'll see you at our next event. Thank you.
Bye, everyone. Thanks a lot.